And I need to do a
Dad.
share screen with you. Okay. Now, I believe this is where we ended last time. We've done all of the analysis of the spectrum of hydrogen, and we did that strictly mathematical. You remember we just took the numbers that we measured for the energy of each one of the lines in the visible spectrum of hydrogen, and we were able to generate a pattern that generated. That was my Find My Phone app. Sometimes it gives a false reading. Okay, but anyhow, this is where we were, and it's important that we did a very simple mathematical analysis of the data that allowed us to do this. Now, shortly, we're going to figure out or look at a way you can actually calculate all of those energy levels without ever looking at a spectrum. And so that's where we'll be going, but we've got a little bit more to do before we can get there. Okay, now, there was a considerable discussion or argument among physicists especially about the nature of light itself. Was light a particle or was it a wave? And the answer to that question is yes, it's both. And it's going to turn out that that's a fundamental characteristic of matter, really. There is a wave associated with it, and there is also a particle, massive, firm, solid particle nature to virtually everything. If we're looking at an individual atom, then we do see both a particle and a wave nature easily. But if you've got a big bunch of atoms, like you might have in a solid bar or something, then each one of those particles has a little bit of a wavelength that's shorter than the diameter of the particle itself. So you don't see the wave nature on a baseball, but you certainly will on a photon. That's its most basic nature. And you will see it, particle nature, easily for electrons, and with a little bit of effort, you can see the wave nature. So that's what we're looking at right now, is trying to look at this nature of matter at the very tiniest fundamental level. De Broglie showed that particles behave like waves. He did a really simple derivation. This is an equation, if you've ever watched a science fiction movie, you've probably seen that. Some scientist somewhere writing E equals mc squared on a whiteboard or blackboard. But this is the relationship for the energy of a particle. We had at first separate laws of the conservation of mass and of the conservation of energy. But Einstein showed that every time you see energy anywhere, it's because mass has disappeared from there and been replaced by its equivalent amount of energy. And he did the derivation and calculated this as the relationship. So the energy you see is the mass that's disappeared times the speed of light squared. So now, if you're burning a Bunsen burner in the lab, you see a few joules of energy. And you can collect all of those reactant molecules and all of the oxides you get in burning it. And if you were to weigh them on any balance we could ever come up with, the weights would be the same. So that was the idea of the law of conservation of mass, that mass in the universe is constant. Every speck of mass that was here in the beginning is still here. And that's true on the level that we can measure generally for energies, really any energy we could find just about on Earth, except maybe an atomic bomb explosion. We can certainly see a disappearance of mass there. But for a candle burning or a piece of magnesium burning in a lab experiment or something, the mass appears to be constant. But there would be a little bit of a change. So anytime you absorb energy, the particle that absorbed it got a little bit heavier. Could you weigh it? Not likely. And so it looks like the law of conservation of mass holds. Most of the time we see energy moving from place to place. That's how we observe it. It's virtually, well, I think it is impossible to measure an absolute energy. We only see energy moving from one place to another. Something loses energy and something gains energy. And sure enough, when we do a careful analysis, we do find that the amount of energy is constant. It really isn't, because if something absorbed energy, it got a little bit heavier by Einstein's equation. But look at the multiplier. It's the speed of light squared. So the speed of light is 3 times 10 to the 8th. You square the 3, you get 9. Square 10 to the 8th, you get 10 to the 16th. So we're roughly 10 to the 17th times that little piece of mass is equal to the energy. So the energy that we can measure in joules or kilojoules around here, the change in mass is so small because you have this humongous multiplier, roughly 10 to the 17th here. So we can't see it, but we believe, because of Einstein's relationships and some ways that we have tested this. For example, in an atomic bomb explosion, there are several kilograms, perhaps, and well, maybe not kilograms. There's several grams at least of mass that disappears when that bomb goes off. And so this equation can be verified fairly easily. And if we look also at another relationship that you and I have looked at already, the energy of a photon of light is h times c divided by lambda. H is Planck's constant, 6.626 times 10 negative 34. C is the speed of light, and that's 3 times 10 to the 8th. And then the wavelength would need to be in meters. And if we put the wavelength in meters instead of nanometers, like we usually measure it, but if we put it in meters, the energy unit we get is joules. Also, in Einstein's equation, the mass has to be in kilograms and the speed of light in meters per second. Then that energy is also in joules. So what de Broglie did was very simple. I don't know, maybe he was doodling in the margin of his PhD thesis. And so he just wrote these two and set them equal to each other. If this one is equal to E and this one is equal to E, they're equal to each other. So if you take that equation now and look at it, you can solve wavelength is h over m times c for photons. So now you see what we've got is an explanation for the dual nature of light. This says that light does have a wavelength. It does travel at the speed of light, but according to this equation, it has a relativistic mass when it's traveling. And so we can just solve for the mass and come up with a mass for a photon as h over lambda times c. So we can actually calculate an equivalent mass for a photon. Now, it's not going to be very much. Remember what Planck's constant is? 6.626 times 10 to the negative 34. And a wavelength is going to be of the order of 10 to the negative 6 or 7 meters for most visible light. And then you got speed of light. So the mass is a fairly tiny amount. We'll get into the actual calculation in a moment. But it does say that photons not only have a wave characteristic, the wavelength, they have a mass associated with them. And so you can get a relativistic mass for photons. Now, photons can't exist except when they travel at the speed of light. And everything, as it speeds up, it becomes more massive. And the ultimate speed is the speed of light. And photons are going to have their ultimate mass all the time that they exist. When they're absorbed, they don't exist. And when we talk about relativistic masses, we're talking about traveling at speeds around the speed of light, in this case, at the speed of light. And photons do have a mass while they're traveling. They have no rest mass. If you imagine a photon at rest, it can't be at rest, but if it were, it would have no mass. It only gets mass as it moves. And so photons are all moving at the speed of light, so they all have a characteristic mass associated with them, and you can calculate it using this equation. Now, we can take the same equation and solve, rearrange it, but the speed of light, particles can't travel at the speed of light. They travel at some other velocity, much less than that generally. So you can calculate a wavelength for photons. And a wavelength, you have a wavelength for photons, you can calculate a wavelength for a massive particle. Now it's going to be tiny. Remember, this is 10 to the negative 34, and the mass of a particle is going to be in the order of well, if it's a fundamental particle, it's maybe 10 to the negative 10 or 6, 10 to 15, something in that range. But you're still going to get a very, very tiny wavelength. And so if you imagine a particle of some diameter, right now I'm holding my hand and my fingers in to make a little sphere to represent the size of an atom. Well, the wavelength of that particle, if it's traveling, at ordinary speeds, the wavelength of that particle is going to be smaller than its own diameter. So when that particle encounters something else, it behaves like a particle. So in order to make that happen, you have to increase this velocity so that the wavelength gets shorter, and the wavelength will get to a size that then can be bigger than its own diameter. When that occurs, you will then observe those particles interacting with each other the way waves would interact with each other. So the wavelength of particles are typically smaller than their own diameter. But if you get a small enough mass and everything, then you can get that wave to get bigger and eventually get to a point where it's bigger than the classical diameter of the particle. It's kind of funny that this equation was, well, actually this was published, and de Broglie did a smart thing. I told you he doodled this in the margins of his PhD thesis, but he erased it and didn't turn it in with his PhD thesis. And that was smart, because if he did, we wouldn't be calling this the de Broglie relationship. It would be known by his professor. And I don't even know who he is, but we all know who de Broglie is. So he did a smart thing. But when he did publish this, in about a month, some people actually scattered electrons off of nickel crystals and was able to measure a wavelength for the electron. And so it actually was measured, and it did confirm this equation. And so this little simple mathematical exercise that we went through here turns out to be very, very fundamental. It allows us to understand why, under some circumstances, something behaves like a particle and something behaves like a wave. Now, I want to make a point here too, that it's not the particle that's changing. The particle or the photon, it is what it is. What changes is what we are measuring. If we have a measuring device that only detects particles, whatever we shoot at it, if it detects anything at all, it's going to behave like a particle. But if we have something that only detects waves and we shoot something at it, its wave nature would be observed, but its particle nature would not. So it's the experiment. Is light a particle or a wave? Yes. Which is it? It's whichever one you measured. If you measure particle properties, it behaves like a particle. You measure wave particles, you would say it's a wave. It's actually both. Okay. Let's look at this. We want to look at the energy of moles of these particles and wavelength and so forth. Now, if you took Avogadro's number of protons, for example, like hydrogen atoms from the periodic chart, that would be 1.01 grams. So Avogadro's number of hydrogen atoms weigh in the order of grams. If you take a mole of electrons and calculate the mass of a mole of electrons, you can look up the mass of an electron in your textbook. You multiply it by Avogadro's number, you get 5.484 times 10⁻⁴ grams. So, 0.5 milligrams essentially for a whole mole of electrons compared to 1 gram there. Now, our eyes are most sensitive to the middle of the visible spectrum is about 650 nanometers. And our eyes are able to see that. And I told you, your typical, our vision cuts off between 400 and 800 nanometers. And you say, well, why would that be? Well, because there's the majority of the light that's coming to the earth to light it up is in that wavelength. Our eyes match essentially in sensitivity the emission distribution of the sun, which is our source of light. Seems to be a pattern. And the sun has a distribution of wavelengths that matches the ability of human eyes to see it. There are radiations outside that, and some insects can see down into the ultraviolet, and some others can go further out into the infrared than we can. But the most sensitive region for our eye is the most intense region of solar radiation. Okay. Now, so if we use this relationship that we've derived, mass is h over lambda c, to get the mass of one photon. So let's plug in the numbers. Planck's constant, 6.626 times 10⁻34 joule seconds. The wavelength, we're dividing by the wavelength, is 640 nanometers. And I want to emphasize again here, don't use that rule you've been taught to move the decimal place. When you convert in the metric system, all you have to do to convert from nanometers is replace the n with 10 to the minus 9. So if you memorize those prefixes, that converts. So when I write this, I'm going to write it in that form, 650 nanometers, because when I'm looking on my computer screen, I can always check to see if I've remembered to do that conversion. And then the speed of light is 3 times 10 to the 8th meters per second. Now, if you deconvolve all of this stuff, it does come out in kilograms. But here is the reason why we use the SI system of units. Because if you express everything in its correct SI unit and you're calculating something, like here I'm calculating a mass. So if I put the energy in joules, which is the SI unit per joules, I put distance in meters, which is the SI unit per length, and I put meters per second as the velocity unit, then I've got all SI units on the right, and I don't have to deconvolve joules to show that the answer is going to be in kilograms. So 2 points. Always do conversions within the metric system just by replacing the prefix with what it's equal to. Don't worry about moving a decimal point 2 places to the right or 2 places to the left if you're going from centimeters to meters. And, you know, even after all this time, I have to sit up and think about that a little bit. But if I've got 250 centimeters and I want to convert that to meters, I'm going to say 250 cent is 10 to the minus 2. 250 times 10 negative 2 is going to be the distance. So do that conversion. Also, second point, make sure that everything you put in where you're doing mathematics is in the proper SI unit. And then look at what you're calculating, and it's going to be in its SI unit. SI unit for mass, remember, is kilograms, not grams. So there we go. We get 3.4 times 10 negative 36, and the units would be kilograms for 1 photon. I've now converted from grams to kilograms and then multiplied by Avogadro's number. And when you do that, you get the mass of a mole of photons is 2.05 times 10 to the negative 9 grams. So if you look back up here, compared to electrons, what is it, 10 to the 5th of the order? So it takes 265,000 moles of photons to equal 1 mole of electrons, and almost 500 million moles of photons to be 1 mole of hydrogen atoms. So you'd have to have 500 million 650 nanometer photons to have a mass of hydrogen, which is 1.01 grams. So essentially 500 million moles of moles. 500 million times 10, 6.02 times 10 to the 23rd, remember? 500 million moles of photons to weigh a gram. So that's the reason why the law of conservation of mass and the law of conservation of energy holds. They're so different that we can't measure them. This checkpoint illustrates that. So let's go through and set it up. And I'll turn on my camera and we'll work it out over here on the side. Okay, now, I hope I can, over the weekend, have time to set up my new camera, and we'll have a little better view, I hope. If not, it'll go back to Amazon. All right. Now, we want to calculate the mass of a mole of photons, and remember we had lambda is equal to h over mc for photons, and for mass that's going to be h over lambda times c. So let's do the calculation then. We've got, well, I guess I needed this one. Yeah. The mass that I want here is going to be 0.001. No, it's one more zero, 0.001 grams. So I've got 1 times 10 to the negative 4 grams is the mass of that we would drop off the balance. And the mass for 650 nanometer light we calculated a while ago, but let's see, that was equal to 6.06 times 10 negative 34, and the wavelength is 650 times 10 minus 9 nanometers, and then we're multiplying by 3 times 10 to the 8 in meters per second. Now, I've not been careful about the significant figures. We've got 3 in all of these numbers, and the speed of light is actually 3.001, I think, or 3.01 times 10 to the 8. So it's good to 3 significant figures as well. So 6.06 with an exponent of negative 34 and divided by 650 with an exponent of negative 9, it was, negative 9. And we're dividing by the speed of light, 3 with an exponent of 8. Okay, so I didn't make a mistake there. I'll double check it. I get the mass of one photon is going to be equal to 5.77 times 10 to the negative 36. And what's the unit? You're right, kilograms. Okay, so now the reason why I'm doing this is I wanted to do a conversion from grams to numbers of photons. So I needed my conversion factor. There is the mass of one photon. So one photon has a mass of this many kilograms. Kilo is 10 to the third. So if I want to write that in grams, it's going to be 5.77 times 10 to the negative 36 kilograms. So, and I want to convert from kilograms to grams. There's 1,000. There's 1,000 grams in 1 kilogram. So I need to multiply that by kilo is 10 to the third. Okay, now, and so that's going to reduce this by 3 powers of 10. So 5.77 times 10 to the negative 33 grams is equal to 1 photon. Okay, now we're ready to do the conversion. If I'm going to take 1 times 10 to the negative 4 grams, and I now do my conversion from 5.77 times 10 to the negative 33, and that was grams for 1 photon. So I want to take this number and divide by the one that's on my calculator screen, 1 with an exponent of 4, minus 4, yeah. 1 exponent minus 4, divide by the answer that I have stored, I'm getting 1.73. The other digits are 2, 6, 7, blah, 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 times 10 to the 31st photons. And now I want to convert from photons to moles. And 1 mole is 6.02 times 10 to the 23rd. Well, it's scribbling, but get up here. So I've got this number on my screen. I need to divide it by Avogadro's number. And Avogadro's number is 6.02 with an exponent of 23. Okay, so what I came out with is, let me see, 1, 2, 3, 4, 5, 6, 7. So I got 2.88 times 10 to the 7th moles. And I wanted you to sort of, this was another exercise. The smallest mass that we can measure at MTSU is 1 times 10⁻⁴ grams, a tenth of a milligram. You'll use those balances in quant if you stay with us and take quant. And the dust that would fall off of that pan, and you not even know it was gone, would be the equivalent of 2.88 times 10 to the 7th moles of photons. So again, I thought this was a good exercise to show you just how small the mass of photons are compared to our own laboratory experience. So you're going to have, you know, what, 10 million moles of photons that would be equivalent to a mass you couldn't weigh. All right. Do you have any questions or anything about that calculation? Now, I did it kind of roughly, but what I would like for you to do is go ahead and work these things out for yourself. And then they are really good. I'm really torn by the fact that we sort of had to not do them the way we've been doing because of the great success you guys have had on exam 1 and exam 1 and quiz 1. So I think a lot of that has to do with doing the checkpoints and keeping up with the course. So do that, and we'll see how we come out for the rest of the course.
Dr. Pearson, would it be possible to get the grade or the answers posted for the checkpoint so we can check our work to see if we got the right answer?
You can work them out, and if you want to, if you get into a problem and you want to submit it to me to let me see what you're doing, just attach them to an email file. It won't matter. I can read them there, but the problem I have is trying to do the actual grading where I'm giving you feedback on them.
Okay. But is there a way to just get the answers posted? Because on some of them, I think I got the right answer, but I just want to double check to make sure I did.
Yeah. Now, the ones that were submitted through Dropbox, I think I've already submitted an evaluation file with all of those, so you can see whether you did it right or not, and on those, the ones that were submitted to me by email, I've got them all graded and everything, but the only way I can get them back to you is by an email attachment. I've done that for some of the ones that came in recently. The ones that came in earlier, I've got graded, and you know, when I catch a little bit of extra time, I'll send those to you if you want me to, from the previous ones. But if you want to work them out and send them to me, I'd be glad to look over them for you and make sure you're on track. Most of the time from now on, I'm going to work with you on them, and perhaps perhaps on some of those we will on some of them I'll let you work, and I'll kind of wait around in the background for a while, and then I'll work through it with you to see if you're on track, and to give you a chance to look at it and say, how do you start that? See, that's an important thing, is knowing where to start and what to do. And as we go along in doing problems, I'll illustrate the methods that I use and the ones that I think will help you a lot as well. Okay, let's continue with the lecture then. Let's see, I did not change my camera. So I've got to go back here and go back to share that screen with you, and then we can pick up. Okay, now the particles that have very, very short wavelengths, and so you can use particles just like you would use light. If you have a biology class or have had biology, the biology department has an electron microscope, and it shoots a stream of electrons, a beam of electrons onto the target that it's trying to, quote, see, and the electrons have very, very short wavelengths, so that means they're going to interact with very, very tiny particles. So while an ordinary light microscope, you can certainly see E. coli and big bacteria and things like that, but most viruses are too small to see with a regular microscope. Some of them can. But with the electron microscope, you can see even viruses and small particles like that. So we can use particles to create a way to image very small objects. Now, if you look at that though, when you have an electron and you're treating it like a wave and it's coming smashing in on those particles that you're trying to see at speeds that approach, well, they're not the speed of light. Electrons couldn't do that, but they could go down to maybe 1% or 2% of the speed of light to get the wavelength that we need. And so you're throwing those waves, but you're also throwing particles. So when that electron is gathering information about the size and treating that like a wave and giving you a picture, it's also impacting that particle, and it's causing the particle to move a little bit. So if it were significant in the moving, we're going to have to choose a wavelength small enough to see the particle and speed up that electron beam enough to do that. But if we speed it up too much, what's going to happen is you're going to start moving the particle. So your image is going to get fuzzy. You're not going to be able to see it as well. So whenever time you locate a particle, you lose some information about the momentum that it had before. So here's a checkpoint that deals with nickel atoms. And it says the diameter of a nickel atom is 248 picometers. Now, in order to see an object, the radiation needs to have a wavelength as big as or longer than the size of the object. The velocity of the electrons needed in order to have a wavelength of 248 picometers. How would you do that? Well, we're going to use the de Broglie relationship for particles. Wavelength is Planck's constant divided by the speed of the mass of the particle times the velocity. So we can solve for the velocity. And that's h is equal h divided by mass of the particle and the wavelength of the particle. Okay, so if the velocity is Planck's constant, 6.626 times 10 negative 34 joule seconds, the mass of the electron is 9.109 times 10 negative 31 kilograms. And the wavelength that we want is the wavelength of the size of the nickel atom. And so that is 248 picometers. Now you see, what I did is I didn't worry about moving decimal places. I just replaced pico with what it's equal to. It's equal to 10 negative 12. So I've got all my numbers now. And by the way, the masses of particles typically are given in kilograms in the table in your book and other places. Most of the time, you don't have to do grams to kilograms. Okay, so we've measured, we've calculated what velocity that would be. That's 2.93 times 10 to the 6. So we're almost 1% of the speed of light. And now, suppose we're traveling. Oh yeah, by the way, I chose that calculation for a reason. I told you the de Broglie relationship was confirmed shortly after he published that. That's the way they did it. They took that equation and they calculated, potential wavelengths for electrons at velocities they could achieve. And they noticed that turned out to be pretty close to the diameter of atoms. And so they started looking around. They found that nickel crystals have atoms about that spacing. So what they did is they took electrons that had a wavelength that would be about the diameter of a nickel atom for this wavelength of particles, electrons, would be about the diameter of the nickel atom, and they expected that beam to be diffracted off the nickel atoms just like light would be. And sure enough, from the spot pattern they got from the reflected electron beams, they could see that yes, that beam of particles coming in had the wavelength of the same as the wavelength of the or the diameter of the nickel atom. And that's how they confirmed it. So it was a very easy experiment to do once somebody knew the relationship, and sure enough, they used it to verify de Broglie's relationship. What's the wavelength of neutrons traveling at some speed? Now, neutrons are much heavier than electrons, so if you had a neutron beam, you ought to be able to see things all the way down to the size of an electron or the size of a proton, not just an atom. You could go 4 or 5 magnitudes lower than that and start looking at fundamental particles if you could do this with neutrons. And by the way, you can. Neutron diffraction is a very common and known technique. Now, neutrons are a little harder to detect. Charged particles are easy to detect. Light is easy to detect. But neutrons have no charge, and they have a very, very tiny mass. And if you've got a neutron beam, often you don't know it's there. You have to do a little bit of fancy stuff in order to detect neutrons. That's a story for physics instead of for chemistry. Okay, let's take a look at that. And we'll go over here and work on that problem. Now, the problem says, what's the wavelength of neutrons? So the wavelength is h over m v, remember, for particles. That's the de Broglie relationship. So all we got to do is plug all of these numbers in. We've got the numbers given. So Planck's constant, 6.626 times 10 negative 34. Now we're going to use that so much you'll probably remember it, but I'll give it to you anytime you need it. So it's not a constant you have to memorize. And the mass of the particle for a neutron is 1.67 times 10 to the negative 27 kilograms. And the velocity is 2.93 times 10 to the 6th. Okay, so there is the plug-in for that. Now, let's think about where do you start, okay? You start when you look at the problem and you say wavelength of a particle. Now, that should clue you that you're looking at the de Broglie relationship for particles. So then you have to have this memorized. Now, you do have to do that. I don't give you relationships like this on quizzes and exams for the unit. If we got to the final exam, yeah, I might give you some of those formulas and things like that. But while we're studying the unit, it's important that you learn the relationships yourself. So in solving problems, the general rule is look at the problem, analyze, and determine what piece of information, what equation, what relationship is implied by that. Then you write down the equation and plug in anything you know and solve for anything you can. Now, when you solve for that anything you can, if it has the units of what you were looking for, that's probably the right answer. If it doesn't have the units of what you're looking for, the rest of the solution method is to do unit conversions. And you keep doing that until the unit of the answer is the unit asked for in the problem, and you can be pretty confident you got it right. Now, that's why it's important to do units, and it's also important to do conversions. You ought to do them the way I showed you. You're going to take a number with a unit that's given. You're going to put that unit in the denominator of your conversion factor, so it'll cancel. You're going to put the unit you know how to go to. Hopefully it's the answer, but you put that unit in the numerator, and then you determine what needs to multiply the numerator unit and the denominator unit to represent the same amount of stuff. And that general principle will work for just a huge variety of problem types. I think I've mentioned, but you can actually do all of the calculations we do in chemistry by unit analysis. Okay, enough of that. All right, so all we got to do is plug in the numbers to this one, and we will get it right, I think. So we got 6.626 with an exponent of negative 34. I'm dividing that by 1.67 with an exponent of minus 27. And I'm dividing that by 2.93 with an exponent of 6. And if I do that, I got a number. I got 1.3541576 times 10 to the negative 13. Now, what's the unit of answer? It's a distance. It's meters. Now, probably if this were a test question, I'd ask you to do that answer in nanometers. So let's do that. Now, I'm going to take my conversion factor. Remember my method. Here's my number. Here's my unit. I'm going to put that unit down here, meters. I'm going to put nanometers up here. That's what I want. There's a 10 to the minus 9 there. I need a 10 to the minus 9 here. Now that's a 1. 1 nanometer, 1 nanometer. So what I've done is calculate like that. So I need to divide my answer by 10 to the negative 9. So I'm going to divide it by 1 with an exponent of minus 9. And I get 1.35 times 10 to the negative 4 nanometers. Now, so you see, that's the size of particles that we could actually see with neutron diffraction. We could go down at, and that speed is what, 2.93 times 10 to the 6 meters per second. Now, I told you it's hard to, we can generate neutrons, but the way we do it is it's a cyclotron type experiment. And what you do is you smash electrons into protons so hard that they fuse and form a neutron. I don't know whether any of you have ever seen this before, but if you've ever seen a field where a lightning bolt struck, or sometimes you can see this effect around a tree that's out in the field where there's some grass under it and stuff like that. If you've ever seen that, what happens is the lightning bolt strikes with more energy than we can get in any cyclotron in the lab in the world. It's perhaps billions of electron volts that the electrons are in that lightning bolt is traveling. And when they hit the ground, they go right into the nucleus of some of the atoms at such speeds that they're able to do that and create neutrons. If you could go within a few seconds of that lightning strike, I don't recommend it, but if you could with a Geiger counter, you could pick up the radiations coming from that spot. And that high flux of radiation kills the grass all the way around it. And so if a lightning bolt strikes the ground, it's going to kill everything around it. If it strikes a tree, you know, it's going to split the tree and knock it all around. But if the tree were in the, had grass or stuff growing around it, it would become radioactive enough at that instant that it would kill most of that grass around it. Now, if you go back a year or so later, you see a remarkable phenomenon in the field. The grass in the middle maybe is still dead, but around the periphery, around the edges of it, it's looked like it's been fertilized in a ring. Well, it has been fertilized. Most people don't know this, but we get more nitrogen fertilizer. What's happening is the lightning, as it's traveling through the air, it's ionizing the nitrogen and making it react with oxygen, and that's giving off light and stuff that we see from the lightning bolt. But it's converting nitrogen and oxygen, which are natural components of our atmosphere. Nitrogen is needed for us to breathe. We have to dilute the oxygen. We couldn't live in pure oxygen. Nitrogen is a perfect diluent for us. It allows us to breathe the air, get the oxygen we need, and by diluting with nitrogen, it's safe at that level. If we had an atmosphere of pure oxygen, we would not have a smoking problem. I can tell you that. Somebody light up a cigarette and it would light them up. The cigarette will almost explode in pure oxygen, and it would probably take a lip or two with it. But anyhow, the nitrogen and oxygen react together in the high temperature of that lightning bolt. That produces oxides of nitrogen. It's raining. The oxides of nitrogen dissolve in water and make nitric acids and nitrates. And nitrates are one of the first number on a bag of fertilizer is the nitrogen number. And it creates fertilizer that fertilizes the ground. So we need the rain, but we need the lightning. The lightning is fertilizing the plants that we're going to go there and eat. Isn't that cool? There's a plan there. Okay. All right. Well, that finishes this segment. So let's take a little break at this time. And I'm going to pause. And then let's go to and I need to now I need to give you this screen. Okay. Need to start. Okay. We've argued and I guess shown to some extent at least that the arrangement of the electrons on the outside of an atom is the most important. Now, I'm holding my two fists up in front of me. On my left hand is a molecule reactant A, and my right hand is reactant B. If you want to follow along, do that. Okay. Now, how are these going to interact with each other? The only way they can is they have to bump into each other. When they bump into each other, what is it that bumps? The electrons. We've talked about that before. The electrons on the outside is really what gives atoms their rigidity. When you start pushing atoms together, even though they may react vigorously with each other, the first interaction that's going to happen is repulsion between those electrons as they start coming together. The electrons on one atom are going to be pushed away from the other one. And in Gen Chem 2, we'll talk about some of the things that does. But we can argue pretty easily that the electrons are what interacts and what causes one atom to react with another one or causes the noble gases not to react at all. It's the electrons. But is it all of the electrons or just some of them? Well, logically, the ones that touch first are going to be the ones that give their characteristics. So we're now going to divide our atom still further. We've got a nucleus that we know chemically is unimportant. For chemistry, you don't need to worry about what's in the nucleus for ordinary chemistry that you do. But the electron around the nucleus, there's really two essential layers. One layer is on the inside and does not interact with anything. We call that the core electrons within an atom. But the ones on the outside are the ones that cause the chemistry. So we call those valence electrons. And it is the valence electrons that give the properties. So we need to know the arrangement of the electrons in the atom in order to determine and understand the properties that atoms have and why on the periodic chart families all behave the way they do. They're all very similar in what they do, and how the properties change across a period from one to the other, that they become completely different. Like on any row down in the middle of the periodic chart, the left-hand side is going to be a very reactive metal. And the right-hand side, the last one on that side, is going to be an extremely unreactive noble gas. And that distinction is happening going across a period. We need to understand that. Now, this was done by Erwin Schrödinger, and he wrote this little equation, H psi equals E psi. Now, this is a differential equation. It's a second order differential equation. So if you're thinking about math, you've probably got college algebra and trig. You're taking that early if you're a freshman. And then if you're a science major, you need to go further on. And really, if you're going to do physical chemistry, you ought to go all the way up to differential equations to understand some of the concepts that's in physical chemistry. It's not required, but it really is good. Just aside, if I were a chemistry major, I'd make sure I'm also a really, really strong math minor, maybe even a double chemistry math major would be really, really helpful, especially if you're headed to graduate school. Okay. But this equation is deceptively simple. It's what we call an operator equation. It says to you, if you will do this operation called H on this thing, an equation, it's called a wave function, but if you will do that operation to that equation, you will get back the same equation, but every term in it will have a constant that can be factored out. And that constant is the energy of the system. Now, this equation actually comes from, I always wondered how in the world Schrödinger came up with this idea to try to treat an atom or a particle like an electron, like a wave in an atom. What would it look like? And one thing I read somewhere was that Schrödinger's hobby was to build organ pipes, organs. And so what he would do is you can use this equation to actually calculate how long a particular organ pipe needs to be in order to generate a certain tone, certain frequency of sound. So it is a well-known differential equation that relates to organ pipes. Now you can go online and find out, you know, and you can make your own wind chimes. Everybody in the world does. They sell them at flea markets all over everywhere. They go down to Home Depot and get a whole bunch of pieces of conduit pipe and cut them off and at certain distances, and you can find out what they are online to generate whatever frequency you want. And then every time that thing gets packed, that tube is going to generate a certain frequency. One of the different lengths is going to generate a different frequency, and so forth. Now, remember the energy levels in hydrogen are quantized. There's only certain energy levels. That is exactly what happens with an organ pipe or with a conduit pipe if you're trying to make a wind chime. If you cut it exactly the length you are supposed to, it will generate a nice ringing tone that will continue. It'll make a good sound and continue to ring. If you make it a little bit shorter or a little bit longer, it becomes more of a thud than a ring. It doesn't resonate and keep that same nice frequency. So there's certain fixed frequencies you get for each one of your organ pipes. And that was just like the energy levels in the hydrogen atom. So maybe that was his thinking. But he wrote this equation. Now, we talked about an operation. If you've had a little bit of calculus or pre-calculus where you've done derivatives, you might know that the derivative of e to the ax is e to the is a e to the x. You see, it's just like this. The derivative, first derivative of a function, e to the ax, is equal to a times e to the ax. You get the function back multiplied by a constant. So that's a real simple illustration of where this comes from. Now, I did it one time. I wrote out the actual form of the Schrodinger equation in spherical polar coordinates. It's the only one that you can solve it. You can't solve it in XYZ coordinates, but you have to use spherical polar coordinates to solve it because the atom is spherical. Hey, take advantage of the shape of what you're trying to model. Okay, so I did that one time, and literally, if we were in the classroom, I could show you. I could have started on one end of the blackboard writing numbers 2 or 3 inches tall, and I would get all the way to the other wall before I got that H function written out. It's a very, very, very complex equation, but it's simple, looks simple. And for us, we don't need to worry about that. Again, if you get into physical chemistry, my guess is they'll actually have you solve the Schrodinger equation for hydrogen. It's a really neat part of the course. So anyhow, this is what the equation looks like. H psi equals E psi. So what he found out that if you do this operation, is the Hamiltonian H is the energy operator. And it has all these differential equations and so forth in it. So it's an energy operator. When you do that to this function, you will get this to occur only for certain functions. That is, some equations, this will work. But you vary the equation just a little bit and it won't work. Again, it's producing equations that would represent, say, the lowest energy state of hydrogen. And then there's another equation that would represent the next energy state of hydrogen. But if you're dealing with hydrogen, there's nothing in between. There's no function between the ground state and the first excited state. So again, this model after the organ pipes is a perfect analogy to what you get in the hydrogen atom. Now, the variables that go into this Hamiltonian operator is the mass and charge of an electron, Planck's constant, and the speed of light. So the only thing he's putting in to represent a hydrogen atom, listen, the only thing he's putting in that represents a hydrogen atom is a mass and a charge of an electron that you can get in the back of your book, Planck's constant, and the speed of light that you can get in the back of your book. He only inputted fundamental constants. And the equation can only be solved for a set of 4 numbers that come up within this wave function psi. Quantization comes out natural. It's just exactly the way the atom is done. Now, there's a model out, and a lot of people, in fact, if you are walking around the MTSU campus and you look over toward the old science building, if you look at that old science building, out in front of it in the big mall courtyard area, and you look back up toward that science building, the new science building would be on, say, way down next to the engineering building or whatever, and you start looking back up that mall, what's straight in front of you would be this building I'm talking about. And it's got a picture of what's supposed to represent an atom, I guess, for the chemistry or physics departments that used to be in there. And it shows an electron traveling in a little orbit. And that was a model that was due to Niels Bohr. It's absolutely wrong, but it's become the image people see. And people think that the way an electron travels is in a little circular orbit like the Earth does around the sun or the moon around the Earth. That's not the case. A lot of work was put in to make that work, and quantization was just arbitrarily assumed. And it defies the laws of physics that say that if a charge moves in a circle, it has to create an electromagnetic wave. It has to create light in some wavelength region, and it has to lose energy in doing that. Well, atoms don't just glow by themselves. They would if the Bohr model was correct, and they would for maybe a microsecond, because as the electron goes in that orbital, if it did that, that orbit and lost energy, it would get closer to the nucleus, and eventually it would spiral right into the nucleus. And the atom wouldn't exist anymore. The proton would fuse with the electron and it would become a neutron. It's not what happens. So that model is absolutely wrong. And this model is absolutely right, but it's treating a hydrogen atom as if it were a wave. Now, is the hydrogen atom a wave? Well, it's going to have a wavelength. We've already seen by de Broglie that that's true. But is it a wave or is it a particle? Well, most of the time you're going to see it as a particle. It's going to be a hydrogen atom. It's got a certain diameter. It's the property you're going to see is more like a particle. But the hydrogen atom has both characteristics. And this model is focusing on the one characteristic that's going to help us explain the chemistry. And quantization comes from this model naturally. You get 4 quantum numbers that's going to describe it. We've seen one of them already. Remember the energy of the hydrogen atom we wrote as the Rydberg constant, R sub h, divided by n squared. That n squared was one of these 4 quantum numbers. N was. Now, when you calculate this energy from this model, you get the wave function that works. Here's what you get. 10 to the 14th is a unit for converting the subunits into the SI unit. 2 pi squared m, mass of the electron, c to the 4th power, speed of light to the 4th power, charge of the electron to the 4th power, divided by the square of the height of the Planck's constant and the square of n that we already saw. So if you take all of this part right here, except the n squared part there, and calculate it, you get 2.18 times 10 to the negative 18. Now again, here's another case that if this doesn't light your fire, your wood's wet. Because look, we didn't put anything in about hydrogen except, well, we didn't put anything at all about hydrogen itself. We put in the mass and charge of an electron, Planck's constant, and the speed of light, and we calculated with this crazy combination of fundamental constants the exact value we got yesterday when we did the simple numerical analysis of the hydrogen atom energy levels. This is outstanding that you could do that you could predict the quantization, that there would only be certain energy levels for atoms, and that you could predict exactly every energy level of the hydrogen atom and never put anything at all in your calculation dealing with hydrogen. The only thing we put in was the mass and charge of an electron, Planck's constant, and the speed of light. And this is a outstanding, amazing result. Now, this quantum number is called the principal quantum number, and we've already seen it has values of 1, 2, 3, 4, 5. It doesn't have a 1.6 or a 3.17. Does not have anything except whole number integers, all the way up to infinity, of course. Now, what this is doing is representing how far this energy level is, or how far the electron is away from the nucleus. So it's giving us a layering of structure we call the shell structure. We're going to get 4 quantum numbers. And so we've got 4 numbers like 3, 7, -4, plus 1/2. That would represent an atom, an electron somewhere. But I've already forgotten what I told you were the numbers. So we use letters to identify that. And it's going to tell you where that electron is, and it's going to be a unique place for every electron in an atom. So if an atom has got 92 protons in it, it's going to have 92 electrons in it, and every single one of them will have a different set of those 4 quantum numbers. We'll get to that a little bit later. But it's going to give us a way of identifying where an electron is in an atom. Now, to show you, I ask you where you live. Well, you're going to give me a street address and a building number and maybe an apartment number. And you could say, I'm in my bedroom or I'm in the kitchen. Another one. So, but you wouldn't say, I'm on street number 13. I'm in house number 7. I'm at apartment number 4. And I'm in my kitchen number 2 or whatever. See, I've already forgot the numbers as well. But you would say you live at 627 Maple Street, apartment 3B. And then you could tell the room if you wanted to, bedroom. And you remember the names like that, but you wouldn't ever remember a whole set of numbers. So that's the reason why these are identified not just by the numbers, but by other letters generally. Now, the lowest energy state of the hydrogen atom, the ground electronic state, is called the K shell. So there's going to be a little layer around the proton, closest to the proton, that electron is in when it's in its ground state. And that is called the K shell. If you excite it, the electron would go up to the next shell, and we call that the L shell. So there's this little layer. Think of an atom now like an onion. And each one of these is a layer of the onion, getting further and further out as we go. So we've got the K shell, the L shell, the M shell, N shell, O shell. This is just alphabetic beginning in K. Why? I have no idea. I don't know. Doesn't matter. But we're going to use large uppercase letters to represent the N values. So instead of saying N is 3, I'm going to say I'm in the M shell. Okay? Or if N is 5, I'm in the O shell. And say, hey, I don't know how to, I don't memorize this table. I wouldn't. If I'm saying I'm in the 5 shell, I'm going to hold up my 5 fingers and I'm going to start with my little pinky. I'm going to say K, L, M, N, O. Oops, I'm in the O shell. Okay? And so that represents, these letters represent these numbers that we put in the denominator for the energy equation. Now, there is another quantum number. It's called the angular momentum quantum number. And it has 0 or 1 or 2 or 3. Now, if you think about, told you the electron isn't in an orbit, but imagine you got a rock on a string. And to keep that rock from falling down, you could swing it around. and you could swing it around with one amount of energy. If you swung it with no angular momentum energy, the string's just hanging straight down. And that's the zero angular momentum position with the rock on the string. But if I swing it around a little higher, it'll come up and it'll level off and swing around at a certain height. If I swing it a little higher, it'll stretch out a little straighter. If I swung it really, really, really fast, the rock would be swinging just in a straight line out from your hand, maybe like David did with Goliath. Okay, so angular momentum, you can have none. You can have 1 unit of angular momentum, or 2 units of angular momentum, or 3 or 4 for the electron in each one of these shells. Now, it turns out there's a limit to that. It's n-1. So if I go to, say, the K shell, the K shell, n is 1. The terminator of this is 1 minus 1, so I only have the first member, 0. So in the K shell, there is the ground state of the hydrogen atom does not have any angular momentum. But the other states do. They have one quantum. Remember, energy is quantized. I told you that from day one. Energy is composed of little pieces of particles. You can have none of them, or you can have 1 of them, or 2 of them, or 3 of them, or 4 of them. Same thing is true for this orbital angular momentum, which is a type of energy. You know, when David let go of that rock, it certainly carried enough energy to bury up in Goliath's head. So it carries energy because of its angular momentum. So the total energy in the system is the energy of that angular momentum part, plus there's an electrostatic energy. You know, the electron is negative. The proton is positive. There is an energy of attraction between positive and negative pieces. So there is always 1 unit of electrostatic energy, no matter what about the angular momentum. And that's the reason for the subtracting 1 here. N is the total energy that includes the angular momentum component of it. And we can't get it all in angular momentum, so we have to stop the angular momentum n value. We have to stop the angular momentum value at n-1. The 1 represents the electrostatic energy because an electron is negative and a proton is positive. And there's always going to be that piece of energy in there. So this stops at n-1. So if I go to the second energy level, okay, the second energy level, the n equal to 2 level, well, this terminates at 2 minus 1. So there is a 0 and 2 minus 1 is a 1. So I have these 2 parts. The first energy level had only 1 part. The second energy level has 2 parts. The third energy level has 3 parts. The fourth energy level has 4 parts. Are you seeing a pattern here? Remember I told you I get goosebumps when I think how simple things really are? When you see this standing right in front of you, you think, well, okay, it could have been simpler if we didn't have that angular momentum piece in there, but we need it. And we had to put it in to correctly describe the hydrogen atom. And it came out of our model, predicting it would be there. So this angular momentum part really messed up things, didn't it? No. The first level has 1 part, no angular momentum. The second level has 2 parts, 1 with no angular momentum and 1 with 1 unit of angular momentum. The third level has 3 parts, 1 with no angular momentum, 1 with 1 unit of angular momentum, and 1 with 2 units of angular momentum. Man, that is so predictable. I mean, it's so simple, it's easy to remember. Okay, now, what this angular momentum part does is it gives you a shape of this region of space. Now, a region of space where an electron is located, we refer to that as an orbital, not an orbit, an orbital, O-R-B-I-T-A-L. It's an orbital. And it has a shape. There's certain shapes possible for that space depending on the angular momentum value. The shape of the first one is spherical. So we use a little S to represent L equal to 0. Just like up here, if I've got N equal to 2, I'm going to call it L. If I'm going to look at the angular momentum 0 level, I'm going to call that an S orbital. And it is spherical, so that helps us to remember. The second one is called P orbitals. The third one is called D orbitals. The fourth one is called F, G, H, I. It's out. S, P, and D are not intuitive, and not. I mean, it's alphabetical after you get to D. No, well, after you get to F, F, G, H, I, and so forth. Notice we left J out, and the reason why they didn't use J is J was already used by physicists to represent an angular momentum of a different type, and so they didn't want confusion about the shape of an orbital and the angular momentum that J had been represented before. So they didn't use J here. Now, it means, actually these first four come from the spectroscopy. The lines that land on an orbital that is an S orbital, like when I drop from the first level all the way down to the ground state of hydrogen, that's going to be, that first ultraviolet line. They are very, very sharp. If you go to the ones with 1, those levels are the brightest lines in the spectrum. They're called the principal lines. If you go to the one with the angular momentum 2, they are, for reasons I'll show you a little bit later, they are diffuse. They're fuzzy. There's lots of little tiny lines within those. And so they're called diffuse, and then fundamental for some reason that I don't remember from spectroscopy, but sharp, principal, diffuse, fundamental were the ones where these 3 letters came from. And then above that, they just go G-H-I-K. Now, I'm going to tell you something I've read in some little, like a Cribs notebook, on chemistry. It was while I was in college, in freshman chemistry, that I went and got the little books to help me pass the course. So there was a little anagram they used for that I still remember. Sober physicists don't find giraffes hiding in kitchens. Hey, it works. I still remember it. SPDFGHIK. Sober physicists don't find giraffes hiding in kitchens. So if I want to go for the third level, L equal to 2, I'm going to say sober physicists don't. That's a D orbital. All right. The third quantum number that comes also directly out of the Schrodinger equation is called the magnetic quantum number. And it has to do with the angular momentum quantum number. Now, we've already rejected an electron like a little sphere traveling around in a little circle. But if you can imagine, now let's take that electron cloud analogy. That cloud could just be spherical and just sitting there. That's L equal to 0, no angular momentum. But that cloud could be rotating. And as it rotates, the charge is moving, and that would create a magnetic field. Anytime you move a charge in a circular path, it creates a magnet. You want to do a little simple experiment with kids? Go to Home Depot or to, I guess Radio Shack would be better, and buy some insulated copper wire, pretty fine insulated copper wire. Then also get a 9-volt battery clip and a 9-volt battery. And then solder one end of that wire to one side of your battery clip. Take the rest of the wire and wrap it tightly and smoothly around a nail, a big, heavy 16 penny or bigger nail. Just wrap it around that till you used up all the wire you bought. And then take the other piece of that other end, and attach it to the other piece of the magnetic of the battery clip. Then clip your 9-volt battery on, and or you can put a switch in it if you want to be real fancy, and in the circuit, so your battery's not on all the time. You can put a switch somewhere in the circuit if you want to do that. And then if you switch the magnet on by connecting the battery, it becomes, if you connect the wires to the battery, it becomes an electromagnet. And, this little simple couple of buck thing, not counting the battery, you can clip it on and put it in a box of paper clips, and they'll stick to it like everything. And kids they'll go, "Ooh," and then you can flip the switch and turn it off, and they all fall, and they go, "Oh!" You can make a kid do oohs and ahs all day with that, and it's really what it's telling us, though, from principles is if the electron does have an angular momentum, means it is moving, it has some kind of path that isn't an orbit, but the average of it does rotate around the axis, it's got to create a magnet. And so there is a magnetic quantum number that's based on the L quantum number. Remember, the angular momentum quantum number was based on the N quantum number. Well, magnetic quantum number only occurs for L greater, for the angular momentum greater than 1 or 0. Okay, now magnets come in two flavors. There's a north pole and a south pole. So you can have all the way from the plus value of L to the minus value of L possible for any given value of L up here. For example, if I have L equal to 0, well, I'm only going to get this first member, this middle member, that one right there, for the M value. So if L is 0, so M is 0. But if L is 1, I'm going to get the next two, a plus 1, 0, and a minus 1. So I'm going to get 3 levels here. I got 1 level here. I got 3 levels here. Looks like things getting messy again. But look at it. When L is 2, I have 0, plus 1, plus 2, minus 1, and minus 2. I have 5 values for the second one. I had 1, 3, 5. Want to guess how many the next one is? You got it. 7, 9. Oh. See? That new complication is still easy to understand and makes perfect sense when you realize angular momentum means that cloud is rotating around an axis, and rotating a charge always creates a magnetic field. So if I were looking at the spectral lines and looking at them, say I got a discharge tube going and I'm looking in a spectroscope to see the lines that we talked about for hydrogen that we saw the other day, I could look at I guess it's that first line in it, coming off of that M equal 2 dropping to M equal 1, I'm sorry, N equal 2 to N equal 1. If I looked at that particular one, the N equal to 2 value would actually have 3 levels, because it would have, this is the first one, this is the second one, but this one would split into 3 pieces as a magnet was present. So if I were looking at that spectral line without a magnet, I'm just going to see one line. But if I brought a magnet up close to it, that spectral line, take your first 3 fingers and hold them so you're looking across them and you just see one. Now, when you bring a magnet up, it looks exactly like it does if you rotate your hand. It'll start out with one line, you bring the magnet up, now you see all 3 fingers. That's the way that happens. That energy level of that second state up there, the L equal to 1 level of that state, that one splits into 3, and you get 3 lines where you had 1. And this is observed in the spectrum, so this absolutely is present and easily seen in the hydrogen atom spectrum. Now there's a 4th quantum number that comes in. The 4th quantum number had to be added, and it has nothing really to do with the hydrogen. It has to do with the fact you're modeling an electron. Now, electrons are fundamental particles. They're a part of all atoms are going to have electrons within them. And whenever everything was created, those electrons that were flung into this universe were spinning. And half of them were spinning clockwise, and half of them were spinning counterclockwise. That represents 2 different spin states. Every fundamental particle has a spin condition, but the spin value for some particles is 0. For example, a neutron has a 0 spin. An electron has a spin, and a proton has a spin. And if they are spinning in a way that the negative particle attracts the positive particle, let's say it that way. If they're spinning like that, the spin of the electron is going to be, say, 1 value. The other particle, the proton, is the spin of the opposite value. When you bring those 2 together, the spins cancel to make a neutron. That's why a neutron has no spin. It's made of a spin plus and a spin minus particle that fuse together to cancel spin. So the neutron has no spin, and one of the most important instruments that you're going to have in understanding the structure of molecules is called a nuclear magnetic resonance spectrometer. We are fortunate at MTSU, believe me. We've got 2. We've got a very good one, extremely good one, that you're going to use in organic chemistry. And we've got another one that you can use for research that's a lot better. So we got a good one for you, and we got a better one for your research. And we've got 2 here at MTSU. If you go to a community college or anything like that, they'll give you the results when they teach organic chemistry for the NMR spectrum. But you are going to get to take your sample, climb up a little ladder, and put that little sample vial into the nuclear magnetic resonance instrument and run the spectrum yourself. And I think that is so, so cool. It makes the organic chemistry at MTSU really, really unique. That's an experience not very many sophomore students are going to get in college. You'd have to get to graduate school, most places, to be allowed even close to the NMR machine. They used to call it nuclear magnetic resonance in hospitals because it can be also used to image, essentially it's imaging water, but don't worry about it. It looks like tissue. So it gives you a much better image of soft tissue than x-rays or ultrasound or anything else. It's terribly expensive because I think the people that built the first machines were way too greedy. They priced themselves out of the market now so that you're not going to get a MRI, they call it, without the doctor really making a strong argument to your insurance company before they're going to pay for it. And because of that terrible expense, we have refined ultrasound to the point where we can get pretty good images from ultrasound. Most of the time, you really don't need an NMR, but that's because they really, really refined the ultrasound technique, and they really, really refined the computer programs that analyze it and produce the images. So they would never have done that if the MRI hadn't been so expensive. Same thing with x-rays. You can do low energy x-rays now can give you a pretty good image of even tissue. So the MRIs priced themselves out of business, except for very expensive, very rare usage. Now the NMR machine and CT CAT scan, that's the x-ray, they put you through a tube, and around that tube in the NMR machine is this extremely powerful magnet. It's usually, in magnetic field strength, it's like 6 Tesla. That's a huge magnet. It's so strong that you're not going to go in that room, and nobody's going to go in that room with anything metallic or anything magnetic on their body. So you're not going to, if you walked into that room with your credit cards in your pocket, it would erase all those magnetic strips on your credit card. And I've heard a story of a janitor who came in to clean, and I guess they didn't know better. They weren't supposed to go into the room where the MRI was, but they went in. When they walked through the door, the magnet jerked his bucket, his mop bucket and mop out of his hand, flew across the room, and crushed into the magnet. And the magnet is held with liquid nitrogen temperatures at 4 degrees above absolute zero. It destroyed a multi-million-dollar machine. I imagine he was no longer a janitor for that place again. And when you use the NMR machine at MTSU, if you can leave your guys, you can leave your credit cards and stuff and wallet in your pants, and if you walk into that straight in toward the magnet, straight toward it, and you climb straight up the steps and put your sample in, back down the steps in a straight line, it'll leave your cards alone. But if you get up there at the top and you wiggle around a little bit, your cards will be erased. So be very careful about that. It's a very beautiful machine, and it works on nuclear spins. The fact that neutrons have no spin and protons do have a spin, it's able to see hydrogens very, very well. And there are probes we can get for it that we can see other elements as well. There's a C13 NMR that carbon-14 doesn't have nuclear spin, carbon-13 does. And so we can do a carbon-13 NMR. If you've got carbon in your body, you've got a little bit of carbon-13 in it anyhow. So we can still see carbon atoms that way. And phosphorus-31, we can see that with NMR and several others as well. So we can detect a lot of different elements by the same nuclear magnetic resonance spectroscopy. But it's all based on this 4th quantum number spin. So this is such a weird thing to me. I don't understand it. But if you've got a molecule that's a great big long molecule, maybe 100 atoms, and on the left-hand side there is an atom, there is a plus 1/2 spin. on one of the atoms or electrons or something. The atom on the other end, hundreds or thousands of atoms away, knows that the spin on that one up there is plus 1/2. How that's communicated, I have no idea. I've read a story of someone that claimed to have found spin correlations several miles. I think the number was like 11 or 13 miles away. And I have no idea how that's possible. It seems to be instantaneously transmitted, because if you do something to that spin on one end, the other one knows it immediately. I don't know how that happens, but it is a very, very fundamental thing about nature, and very useful to us that spin exists. And we had to put that spin quantum number in. Now I want you to remember, the spacing between two energy levels is what? 1 quantum of energy. Okay, so if the difference between spinning clockwise and counterclockwise is 1 unit, well, the spin of one of the levels has to be plus 1/2, and the spin of the other one has to be minus 1/2, so that the difference between the clockwise spin and the counterclockwise spin is 1 quantum. That's why the spin for electrons is either plus 1/2 or minus 1/2. And that's independent of all of the other quantum numbers we've seen. This one didn't come out of the Schrodinger model. It had to be added in later as we started to encounter spin, and you'll see why we had needed it right away when we start assigning quantum numbers to energy levels. Okay, so for any given value of n, there are different values of L. So if n is 3, there's going to be 3 values of L. We know that if n is 3, you have 0, 1, and 2 for the 3 possible values of L. So it goes to n minus 1. For any value of L, there's going to be 2L plus 1 different values of M. Now, the 2L plus 1, remember on that little pattern that I have, you've got from here to here is L values, L of them. From here to here is L values of them. There's the 1, the extra one, the 0. So it's 2L plus 1 different values of M for any given value of L. And then the spin has 2 values independent of the others. It's either going to be plus 1/2 or minus 1/2. Now, we're going to describe, like I'd say, where do you live? 627 Maple Street, okay? We're going to define an orbital name by the value of n and L. For example, the first value is n equal to 1, L is equal to 0. So that one is called the 1s orbital. That is the ground state of hydrogen. The next energy level is the n equal to 2. And at n equal to 2, you can have L equal to 0 and L equal to 1. So you can have a 2s and a 2p orbital. When n is equal to 3, you can have a 3s, a 3p, and a 3d. You're adding one more in that sequence as we go up. Next one, what? 4s, 4p, 4d. Next one, 5s, 5p, 5d, 5f. You know, so we can get that pattern just by the values of n and L. And so the ground state is called the 1s orbital. That was the K shell. The L shell is n equal to 2, and it's made of the 2s and 2p. The next level, now K, L, M, the M shell is 3s, 3p, and 3d, and so forth. The energy of an orbital is determined by the sum of n plus L. Remember, orbital angular momentum is a energy, and n represents energy, electrostatic energy. And so the value of n plus L is this total energy of a particular orbital. So I'm going to add n plus L. N plus 0 is 1. N plus 0 is 2. N plus 1, 2 plus 1 is 3. 3 plus 0 is 3. So both of these two have the same value of n plus L. In that case, the lower value of n is lower in energy. So the 2p is lower in energy than the 3s, and so forth. There are other places where two orbitals may have the same value of n plus L. All right. Now, this is a checkpoint. Let's go ahead with it. And there are 4 quantum numbers, n, L, m, and s. Now they are better described as m sub L, meaning magnetic quantum number based on L, and m sub s, a magnetic quantum number based on spin. So the better way to designate them is n, L, m sub L, and m sub s. I think is more descriptive. But if you just wanted to call n, L, m, s, I'm good with that too. That's okay. So we're going to list all the values of L, M, and S when N is 3. Okay. Now, let's see if we can generate that over here where you can see it. Okay. Let me get this. Okay. And okay. All right. Now our problem was I want all of the quantum numbers for n, we said is 3. And if n is equal to 3, let's remind ourselves what we can have for L. L goes all the way up to n minus 1. So I'm going to go 0, 1, and 2. Now remember, if that's a 3, there has to be 3 of these. Okay. Now, for each value of L, there's m goes from the plus value of L to 0 to the minus value of L. Okay, so, and then spin is going to be either plus 1/2 or minus 1/2. For any value up there, it doesn't matter. We're always going to have a plus spin value and a minus spin value for each one of those up there. So now, let's just go about doing them. Suppose n is 3 for all of them. Let's take this one. So when n is 3, I can have an L equal to 0. When L is equal to 0, I can have a range of values of m that go from plus L to minus L. So from plus 0 to minus 0 is just 0. So m can be equal to 0. Now, this one would be called the 3p state. Okay. And now there's a spin value. I can have s, or m sub s, equal plus 1/2. But I could also have n equal to 3, and L equal to 0, and m equal to 0, and s equal to plus 1/2 to minus 1/2. So there's 2 electrons that can be in that particular piece of the 3p set. One with plus 1/2 spin and one with minus 1/2 spin. So I've got this one with this one. Now let's go this one with this one. So when n is 3 and L is equal to 1. Now, what are the values of m? When L is 1, we go from plus L plus 1, 0 to minus 1. So I can have L equal to plus 1. And for that one, I could have a spin equal to plus 1/2. Or for that one, that should have been an m. And m equal plus 1. And spin equal to minus 1/2. Okay, so I've taken the n equal to 3, the L equal to 1, and the m equal to plus 1 piece. Now let's do the m equal to 0 piece. So I've got n equals 3, L equals to 1, m equals to 0, s equals to plus 1/2. And n equal to 3, L equal to 1, m equal to 0, and s equal to minus 1/2. Okay, there's a third one now. We've got to go minus 1. So I can have n equal to 3, L equal to 1, m equal to minus 1, s equal to plus 1/2. I can also have n equal to 3 with L equal to 1, m equal to minus 1, and s equal to minus 1/2. Now, while we're here, now you see what I have done here is, I'm sorry, I told you this one right here, I was right. This is the 3s orbital. Hey, you ought to catch me when I make stupid mistakes. This bunch we're doing here is the 3p state, okay? But that was the 3s, 3p state that we've done right here. And that exhausts all of the possible values for the L equal to 1. I can have plus 1, 0, and minus 1, and spin plus or minus 1/2 for each one of those. And notice right here, there are 2 values. And notice right here, there's 2, 4, 6 values. All right, I'm going to need a new piece of paper to do the next one because it's going to be bigger. So look up at the grade on the checkpoint. How many points is it worth? How many pieces do you think it's going to have? Well, we've got 8 of them done. How many more do we need? Right, 10. All right, so now let's go. And we're going to do, this time, n is equal to 3. And L is going to be equal, n is equal to 3. L is going to be equal to 2. S is going to be equal to plus 1/2. And now that you brung it up, we are always going to assign positive quantum numbers before negative quantum numbers. So if I got positive, 0, and negative, they're going to be ordered that way. I'm going to do positive first, 0 next, negative last. That's the order we do them. Now, if you Google stuff, they're probably going to do it for you the other way or some different way. Some may do it right, some may do it wrong, depending on the website you're in, I guess. Oh. Okay, so, oh, I left off M, didn't I? Oops. All right. Let's back up and point. Okay, we've got n equal to 3. We've got L is equal to 2. And now, the m values. It goes from the positive value of L to the negative. So it's going to do +2, +1, 0, -1, -2. So the m is going to be +2, put the sign in, and the spin is going to be equal to +1/2 for the first one that I'm going to list. Now I'm going to do the other one of that pair, 3, L equals to 2, M equals to +2, and S equals to -1/2. Okay, now I've taken care of the 2 value for M. The next value is 1. So with N is equal to 3, L can be equal to 2, M can be equal to +1, spin can be equal to +1/2, or I can have N equals to 3, L equal to 2, M equal to +1, S equal to -1/2. And now N equals to 3, L equals to 2, M equals to, the next value would be 2, 1, 0. S is equal to +1/2. N equal to 3. L equal to 2. M equal to 0. And S equal to -1/2. Now we got to go to the last, or the next value. And that would be, again, N equal to 3. But L is equal to 2. And now M would be the next value I've used. I've used the +2, +1, 0, so it's going to be -1. S equal to +1/2. N equal to 3. L equal to 2. M equal to, again, -1. And spin equal to -1/2. Now, so I've used +2, +1, 0, -1. I got one more value for M. N equal to 3. L equal to 2. M equal to -2. S equal to +1/2. And I can have N equal to 3. I can have L equal to 2. I can have M equal to -2. And S equal to -1/2. Okay. Now, these are called 3D orbitals. So this is the 3D set of orbitals. And how many are there? 2, 4, 6, 8, 10. Hence the grade. For this checkpoint would have been 2 parts here, 6 parts here, 10 parts here. That's 18 altogether. Now, I want to, whoopsie daisy. I want to back that up. I didn't mean for it to jump over there just yet. Where is my periodic table, Earl? It's among all these papers here. I'll tell you what I'm going to do. I'm going to show you where you can always find a periodic table. Right there, inside my textbook cover. Now, look at what we got up here. We had 2. How many columns are there? You got it, 2. Then we had 6. How many columns are there here? 1, 2, 3, 4, 5, 6. Then we had 10. How many columns are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know, I'll bet this stuff is related to this stuff. And if we did the 4 set of quantum numbers, how many do you think we're going to get? Well, I bet you it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We would have 14 more values just like we did here. That would be a little bit extensive. I wouldn't ask you to do that because, hey, if you understand what we've done here, you understand it all. So this one is a really important checkpoint. Now, I hope you will practice this yourself. Just pick an arbitrary number. Now, if you can see, when I went up to 3, I got a total of 18 columns. You know what? There's something funny about that. 18, how could I represent that? 2 times 3 squared, 3. 2 times n squared. 2n squared is the number I'm going to get for the total of any level. So if I'm doing the third principal quantum level, third principal quantum level. Now, which one would that be? Let's see. Third one would be K, L, M. So if I'm doing the M shell, that's 3. I'm going to get 18 columns, 2 times 3 squared. I'm going to get 18 different values possible. So if you want to try to do the fourth one, what are you going to get? Well, 4 squared is 16. 2 times 16 is 32. So if my checkpoint had 32, had all of them up through 4, we would have had 32 values total. So that's a lot. All right, so now, so we know what they are looking like. And remember now, the orbital itself is defined by the value of n and L. That describes the orbital. And so these 3D orbitals, move my periodic table, but that's the first row across the d orbital set. Now let's go and look at how you go about identifying the electron configuration. Okay. Now, an orbital itself is a region of space of volume with a definite shape. And there can be 2 electrons in that shape. There is a wave function psi for that state that has variables in it. It has x, y, and z and time, just to think about 3-dimensional systems. But actually, in the way it was actually solved by Schrodinger, you have to put in spherical polar coordinates. And instead of x, y, and z, it's r, theta, and phi. And if you don't know what that means, just don't worry about it. It doesn't matter if you've never seen it before. But that completely describes the way the system represented by that psi. Now, let's make a point. The hydrogen atom can absolutely be described. Every bit of its behavior, every single bit of it, can be described by this wave function. If you want to know anything about the ground state, hydrogen atoms at room temperature, anything that you could ever want to know is contained within that wave function for the ground state. And if you look in your textbook, I think it gives the actual equations in spherical polar coordinates for some of the actual wave functions or equations for some of those states of hydrogen are in there. And it perfectly describes hydrogen. Now, is hydrogen a wave? Well, of course it's not. Is it a particle? Yes, most of the time it behaves just like a particle. And the equation describes the behavior of hydrogen perfectly, but it doesn't mean hydrogen is an equation. Of course not. But hydrogen atoms do the same thing that equation does. The real hydrogen atoms out here in our laboratory do exactly the same thing that is done in the computer when you do this wave function and have it do stuff. It'll be mirrored exactly by the way the hydrogen atoms behave. So sometimes we get kind of confused and think that, well, hydrogen really is a wave function or an equation. No, it's not. A hydrogen atom is a hydrogen atom. It's not changed. It It's just that the model is a perfect replica of the behavior of hydrogen. Does that make sense? I hope so. Okay. Now, one of the funny things about the hydrogen wave functions is they do contain imaginary terms. Now, by imaginary terms, if you've had some layers of math, the square root of a negative number is impossible. You can't take two negative numbers and take the square root of them, because when you square any number, whether it's positive or negative, you get a positive value. So you can't take the square root of a negative number, but you can represent a number in general as a plus ib, where I is the square root of -1. So a real number can be represented as a real value, a, and an imaginary value, I square root of 1 minus 1 times b. Now, anything you're going to measure depends only on the real part of the number. The imaginary part mostly is invisible unless you're doing something that has to do with the square of the number. Because if you took a plus ib and squared it, you would take the square of a would be a squared, but the square of the ib term would be minus b squared. So you get a squared minus b squared if you squared that number. You're wondering about the cross terms. It's a plus ib times a minus ib is the way you do the square. The cross terms cancel. But, that's part of math. You don't need it in chemistry. But anyhow, what I want to get at is if you have the square of the wave function being important, the things that depend on the square of the wave function have a contribution from the imaginary part of the wave function. So here's a real value. The square of the wave function represents a real measurement, but it depends on the imaginary part of the wave function as well. So this is the one place that I know of that you might have wondered if you've had math, what in the world good is imaginary numbers? If they're not real, what good are they? Well, there are things that depend on the imaginary part of the number. Squaring of a wave function is always going to produce a positive real value. So that means that anything you can measure about hydrogen has to depend on the square of the wave function. Now, what the square of the wave function is, it's proportional to the probability that the electron in this atom, represented by the wave function, is located at some point in space and time, x, y, z, and t. So if I want to know the probability of an electron being 3 nanometers from the nucleus in the ground state, all I need to do is take the ground state of the hydrogen atom and square it. And then for the radius parameter, I'll put in r squared. And that's whatever I've said, 5 nanometers, or that would be 25 would be the number that would go in there in the square. And I could calculate a value. So the probability of finding an electron depends on whether it's likely to be there or not. That's psi squared. But it also depends on the volume of the probe you're using. So if I'm going to think about a Geiger counter and I'm trying to locate a piece of uranium, well, the probability of that Geiger counter clicking depends on the square of the intensity of that radiation times the distance you are away from it. As you move that probe in, it's going to get louder and louder. So it's going to be out here, it's going to be click, 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 click. And then as you go closer, it's going to go click, 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 click. As you get closer. Well, imagine an electron Geiger counter that clicks every time the electron goes through the probe. What's the probability of that probe clicking? Well, it's the square of the wave function at any point, any distance away from the nucleus. So I'm moving my probe up to some distance. As I move it closer, it's going to get bigger. because the wave function squared gets bigger as you get closer to the nucleus. It's much more intense at the nucleus. And then you have to multiply it by the volume of the probe. And so what I've done here is I've said, okay, pi r squared is the diameter of the end of the probe, and delta r is the thickness of the probe, how much of the distance away from the nucleus the probe is actually occupying. So 4 pi r squared delta r would be the probe volume contribution to whether it clicks or not, whether you've got a big probe or a little probe. Little probe's not going to click very much.
Dr. Pearson?
Yes.
Are you looking at the slides because we're still seeing the problem you worked out earlier?
I am so sorry. Yes.
That's okay. Thank you.
Yell at me now anytime. Okay. Okay, there you go. Now you're looking at what I'm looking at, and I'll get this running. And here's what I have been saying. So the orbital is the region of space with a definite shape. There's 2 electrons that could be located in that orbital. It's defined by a wave function. The wave function is an equation in x, y, z, and time, or it's a r theta phi and time. It can have imaginary terms, but when you square an imaginary number, you get a real number, a real positive number. And the square of the wave function is going to be proportional to the electron being located at some distance away from the nucleus. So if I had a number, say the wave function is 5 at some place, square of it would be 25. So those 25 values, I can arrange that wave function so if I added them all the way up from coming into infinity right into the nucleus, say that would be 1. That would mean that if the wave function has a value at some point, it's been changed so that the total of all the possible places the electron could be is 1. Because the probability of it being in the universe is 1. So that square of the wave function then is proportional to the probability of the electron being at some location. And in the example where it's squared to 25, it would be divided by the sum of all of those squares to give me a number fraction that would represent whether that Geiger counter is apt to click or not. And I said it depends on the size of the probe. If the probe is bigger, it's going to pick up more of the clicks. Say, if I had a probe so big that the whole hydrogen atom was inside it, it would be clicking all the time. The electron's in there all of the time. But if I shrink my probe down, and it makes sense, it has to get smaller than the atom itself in order for you to probe what's inside the atom. So you have to use a very tiny probe. What's the likelihood your probe is going to click? Well, it's going to be the square of the wave function times the volume of the probe that's inside the atom. And that's what this little 4 pi r squared term means. Now, it does turn out that the wave function can be 0 somewhere. That's called a node. Remember when we talked about the organ pipes? The reason why you get the standing wave for a certain length is that the reflected wave and the transmitted wave are in phase with each other, and you wind up amplifying the sound. But if you cut that wave wrong, the transmitted wave and the reflected waves can actually cancel each other out. So that when you hit that little wind chime, if it's cut wrong, it'll just thud. Well, that's the same thing here. There are points where the wave is 0, and those are called nodes. I used to do a little bit of picking and grinning, and most of the time, while I was picking and grinning, everybody else was laughing out loud. But if you really want to tune a guitar the best way, you can use a strobe to do that. And you strobe at a certain frequency for that string, And then when you pluck it, that string will appear to be waved, and it'll appear to like, say, the lowest frequency, which you'd never get even on the bass string, but the lowest frequency you could have, the wave would start on the left end of the guitar and go to the right end, and it would curve up, and then the reflected wave would curve down. So when you look at it, it would look like the string was just vibrating up and down between those. If you strobed it at the frequency of that up and down movement, the strobe would only come on at one particular instant, and it would do that at the same time in every cycle, and it would look like the string was just permanently bent into a shape. That is the perfect tune. When you tune that guitar to seeing that standing wave, not traveling, but just sitting still, but wavy, then you've got it tuned perfectly. And if you do that, the way the little frets on the guitar neck are spaced, they will be spaced over the points where that wave isn't moving. Like if it's vibrating up and down, on one side of one of those points, the string will be going up at the time across that point it's going down. And so it'll go back and forth, but there'll be a point there that doesn't move at all. If that's on a guitar, the fret that you want to if it's made right, the fret will be exactly under that non-moving point of the string. It's called a node. And that means that when you get ready to chord that string at that fret, if you put your finger straight onto the string at that fret, you can push it down and change the frequency of the sound. Generally, that's going to make it higher frequency. You can put your finger on that and you hear nothing, no chatter. Now, if you ever notice somebody learning to play a guitar, it chatters all the time when they're fingering it. They know to press at a certain fret, but they haven't learned yet exactly the point on the string they need to put their finger on to fret at that fret. And so these nodes exist, and they exist in atoms as well. There are places in the atom where the wave function is 0, which means since the probability 0 squared is 0, the probability then is 0 that you would ever find the electron at that position. That's kind of weird, and we'll talk about that more in a little moment. But that is a node. Now, the value of n is also the number of nodes that particular orbital is going to have. The n equal to 0 state only has one node, and it's at infinity. The electron is going to be in this space somewhere, but it can be anywhere in the ground state. Now, let me give you a weird example. There's a tank of hydrogen in the laboratory at MTSU. It's still there, I think. There is a finite non-zero probability that one of the electrons on one of the hydrogen atoms in that tank of hydrogen is in the room with you right now. Now, will you ever find it? Probability is so low that no, you won't. But the hydrogen atom ground state is only bound at infinity. It only goes to 0 at infinity, and that's true for every state. Every state of the hydrogen atom is going to be bound at infinity because we're just requiring that hydrogen stay in this universe. Electron can't get out of this universe, but it could be anywhere within it, but with a different probability. The probability that it's near the atom in that tank is really high. The probability that it's outside the tank at all is so low nobody would ever find it. But if suddenly a hydrogen atom appeared out in the lab, it could happen, but it's sort of like if I saw that happen, I'm not telling anybody that hydrogen atoms just appeared and I saw them materialize right there in front of me. I'm not telling people that. You know why? Because people that see things like that, they come and get you and they put one of these big white coats on you with really long sleeves. They tie them in your back, around your back, and they put you in a rubber room. So even though it could happen, I ain't telling nobody if it happens to me. Okay, let's look at the shape of orbitals. And here we go. The 1s state. If you have the computer plot out the chi-squared value for the wave function versus r, it comes out to be a sphere. That's what we expected it to be. Now, an equation will evaluate to a sign, a mathematical sign, not a charge. We're talking about a mathematical sign. In the wave function, anywhere in the universe, the square of the wave function and the wave function itself is positive. So if I put in any, go to your book, locate the 1s orbital wave function, put any value of r in that you want to, square it, you'll get a positive number. It's going to always be that case. So the 1s orbital is a sphere and it has a mathematical sign of plus. So no matter what value of x, y, and z you put into the hydrogen atom, when you evaluate the equation, you'll get a positive number. It does have one node, it's at infinity. So this thing just gets, I can't do it on the model I draw here in PowerPoint, but the shading should be very intense here and get lighter and lighter and lighter and lighter and lighter. And it would get to zero intensity when we got it to infinity. But sometimes what we do is we draw a circle of a radius that includes 90% of the probability. And you can calculate what that is from the wave function. And then you can draw a model that has something like that shape and that size. And you could make it proportional so that, you know, if you made this s orbital one size and the 1s orbital one size and the 2s orbital a different size, you could scale it so that the 1s orbital of hydrogen could be the size of a marble and the 2s might be the size of a tennis ball or something. You know, you can scale them and draw models and build models. In fact, we build atomic models like that, and you can buy a set of them that are so good that if you can't put them together in three-dimensional space and build a molecule of these models like we did with the nuts and bolts thing, if you can't build it with that model set, you can't make it in the lab either. So don't even try. They're that good. We've got modeling that good. But the 1s orbital is spherical. It only disappears at infinity. And there is a 90% volume probability that we can use to represent the size of the atom. Now, if we do the graph, the 1s orbital wave function looks like this when it's graphed. So it has a high value at the nucleus. Listen, a high value in the nucleus and a low value that drops off exponentially as you go out. Now, if I square that, you square any number, you get a bigger positive number. So in this case, the square of the wave function would look like that. So the most probable place for an electron in the 1s orbital to be is where? Inside the nucleus. Oops. That probably rocks some boats. Now, what's the probability you're ever going to find it there? Well, I have to multiply that by 4 pi r squared delta r. Now, the r value here at the nucleus is 0. So your probe has to shrink to 0 volume to get inside the nucleus. And so it never clicks. You're not going to get any, find any electron actually inside the nucleus. Not because it isn't there, but because your probe has to go to a mathematical point. In this model, The nucleus is not a little thing of a certain diameter. It's a mathematical zero volume point, is the way that was treated. So you're not going to find an electron in the nucleus, although that's the most likely place for it to be at any moment. And so the square of the wave function times the probe volume looks like that. And the most probable number would be this much. So for example, if I'm saying, well, how big are hydrogen atoms? What I could do is I could bounce them off a surface. And if I followed the center of mass of that hydrogen atom, it would get to some minimum distance from the nucleus before it bounced off. So I could look at the scatter pattern and tell how big that particle was that was hitting the surface. So we can do electrons or hydrogen atom scattering experiments. And if you measure then the radius or the diameter of the hydrogen atom from those scattering experiments, and you did like Millikan did with his oil drop experiment, and we've just done, if you just rank them from highest to lowest and look at the numbers, the number you see in that stack the most often is this value right here, which you can calculate. And guess what? If we use the 1s orbital of hydrogen and do this calculation and predict that distance would be the average radius of a hydrogen atom, you predict that and measure it, perfect agreement. The model is absolutely correct, does work. And scattering experiments like that verify the prediction of, so the most probable, the number you're going to get most often in a scattering experiment with hydrogen atoms will be this one right down here. And we can calculate that. We just find the maximum in this curve. And that's it right there. Now, if you average all your numbers together, you get an average distance. It's going to be a little bit bigger than the most probable one because the area on each side of this has to be the same. And this thing only dies at infinity. So that means the average is going to be over to the right of the most probable distance. And again, you can calculate that. You can measure, do the measurements we talked about. You can find which number appears the most. That's going to be most probable. Average them up. That's going to be this distance. When we mathematically determine the average value from the Schrodinger model, we get this distance, and experiment is perfect. It agrees exactly to this. So I'm making the point that the hydrogen atom, wave function description of the hydrogen atom is perfect. Every time it's been tried, it's been correct. And it's become the standard now. To get the diameter or radius of the average hydrogen atom, nobody does the experiment anymore. They just calculate what it would be from the Schrodinger model. They don't need to do the experiment. And if I did that experiment and I came up with a number, I'm really, really careful. I'm really, really accurate. And I came up with a number different than what's predicted by the quantum mechanical model, I wouldn't tell anybody that either. Wouldn't do any good. Nobody in the world would believe me because this model works so good everywhere it's been tried. In the areas where you can't measure it, really, we believe the predictions of the quantum model, even though we might not be able to measure it ourselves. We're still going to think we know the answer, and frankly, we do. Now, the 2s energy state, what does it look like? Well, it's made of two parts. Remember? N equal 2 parts. There's a part here and a part here to the wave function. Now, if you put in any value of x, y, and z inside this region I'm circling right now, this outside layer, and evaluate it, you'll get a negative number. And if you put any value inside this lighter volume and evaluate it, you'll get a positive number. What happens when you go from positive to negative? you get a 0. That's called a node. So there is an interior node in the 2s state of the hydrogen atom. Now, what does that mean? It means that an electron you'll never ever find a hydrogen atom this size. You'll never find a hydrogen atom that is a diameter equal to the diameter of that little circle. Never in any of your experiments. You do the numbers, you do the scattering experiment and look at all the numbers, you'll find these numbers inside here a lot in your data. You'll find these numbers out here a lot in your data, but you will never find a single one that size. That's because the wave function is a node, and real hydrogen atoms aren't equations, but they're going to do exactly what this model predicts. Model predicts you can't find one that size, and when you do the experiment, you don't find one that size. The second node, of course, is in infinity. We've got to close the universe for that electron. It can't be, it's got to stay inside this universe. So again, now, let's see how the equation would give this kind of pattern. Well, if you're in close to the nucleus, you have a positive value. As you come back out, you go negative and you go through 0. This distance here is the distance from the nucleus out to that node. That's where the 0 is. You see, in looking at an equation, it makes perfect sense. You got a positive value, you go to 0, go negative. There's a smooth transition as you go all the way out. And of course, it's got to come back up to 0 because you've got to have the wave function 0 at infinity. So I got positive to negative. Now, the square of the wave function. Well, you square a negative number, you get a bigger positive number. So the square of the wave function looks like this. It's also most probable distance is at the nucleus. So in the s orbitals, they can all penetrate the nucleus. So I get this wave function, and I do get a value for the probability everywhere except at infinity and that distance. Now, if you multiply that by the probe volume, then you're going to get something that looks like this, because your probe is going to go to 0, it's r equal to 0. So you're going to get 2 regions of space where you can find an electron, 2 regions of space, one here and one here, one here and one here, where you can find an electron. And again, you can predict the most probable distance and the average distance as well. Now, if you do the 2p state, they look like this. Now, if you, and again, you could go into your textbook, find the Schrodinger equation for the 2p orbital, and get that number. There's one of them that would graph just like this. It would look just like this. There's a region up here where the electron can be found. The wave function has a value. The square of the wave function has a value. And since you're not at the nucleus, the probe volume has a value. So you're going to get a volume here and another volume down here for this orbital. So just like the 2s orbital had 2 regions of the volume orbital, 2 pieces of the orbital, the 2p orbital has 2 pieces, one here and one here, separated by a node. Now, you imagine this. Take a piece of paper and imagine that's a node. So you put the paper in your hand and you imagine that's the node of the 2p orbital. And you put your hand above it to represent an electron. So there's an electron in this region that's on this graph I'm showing as plus z region. There's a probability the electron can be there. Now, put your finger under the paper. Down under it, there's a region at the bottom, below the little blue plane that's shown on that graph, where you can find the electron. I'm going to ask you a trick question. How can an electron get from this top region above the plane to the bottom region below the plane without going through the plane? And it can't go around the plane because that plane extends all the way to infinity. The electron can't go outside the universe and come back. So like you did, you took your hand above the paper and put it below the paper by going around the edge. You can't do that in real life with a real hydrogen atom. So you tell me, how does the electron get from above the plane to below the plane without going through the plane? I told you it was a trick question. You know how this was a trick question? I tricked you into thinking of the electron as a particle. A particle can't do that. If you put your finger on the guitar string and press down to one of the frets, if it's tuned correctly, you have standing waves on either side. There is a wave that's occurring there. How does the wave get from one side of that wave, one phase of the wave, to the other side? Well, that's a stupid question. It's a wave. It always exists like that. So something about the nature of hydrogen atoms means that it behaves like this. We can now explain it. The wave doesn't have to go like I tricked you in saying, okay, you take your hand and move it from one side to the other. I focused on it being a hand, a particle moving from one side to the other. Particles can't do that. They can't. But they can behave like a wave and do what the wave does, which means that at some moment in time, you can be looking at hydrogen atoms and you can locate the electron here. And at some other time, you got your probe down here. And sure enough, you see hydrogen atoms with their electrons down here. Now, we can't say, but you see a wave, if the electron is behaving like a wave has a value of the wave here, has a zero value of the wave here. So the square of it down here is the likelihood your probe will catch it down here. The square of the probability wave function here is the probability you'll find it here. In any real experiments, you're going to take your electron Geiger counter and it's going to go click, 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 click. It's going to behave just like that. That doesn't mean there was a particle who appeared and then disappeared and then reappeared. It just means the nature of the hydrogen atom is such that it behaves like a wave. I've really hammered on this point, but I think it's an important understanding. So I hope you're following. So all this means is the wave function will evaluate to a positive number anytime you're above the plus the xy plane. In other words, no matter what the value of the z value on your coordinates, x, y, and z, if z is positive, the wave function is positive. If z is negative, the wave function is negative. And there's a node between the 2 points. So there's a node between them. And in this case, the node is a plane that separates this piece from this piece. Both of these pieces and that node constitute what we call the 2p orbital along the z-axis. Now, the second node, of course, is an infinity. Now, there's going to be 3 of these. There's 2 others. Both of the others look just like this one, except this nodal part is along X on one of them, and the YZ plane becomes the other node, or it becomes an orbital like this one on the y-axis with the XZ plane being the node. Now, oopsie daisy, previous, I want to go back. If someone asked me to sketch the 2px orbital, hey, I'm not going to try to draw this three-dimensional silly thing that looks like that. That's hard. And to draw perspective drawings that make sense and look good. You know, I had enough trouble getting this one to work. And every time I look at it, at one time I'm looking above the plane and the other time I'm looking below it. It kind of flips in perspective for me. But anyhow, if someone tells me to draw the 2px, I'm just going to call that x, and I'm going to, let's see, x, and I would call that x, I'd call that y, and I'd call that z. And that's all. I'm going to draw the same figure. I'm just going to do x, y, and z, like that, for the 2px. If I wanted the 2py, I'm going to put the y up there. And so I'm going to do x, y, and z. So I'm going to draw the same figure, but this would be y, and this would be x, and this one would be z. So I'm not going to try to draw three different perspective models, but in reality, there are three. There's one along here, one along here, and one along here. And that's what the orbitals look like. The 3D orbitals that we just did over here on our chart a while ago, they have a shape too. And there's two different kinds of shapes. There's one of them that looks like this, and it's got another funny little piece. It's sort of like a p orbital that's got a ring of probability in the xy plane. Now remember, the 3pz had nothing in the xy plane. It became a node. But this one does. It's made of these two parts, and it's got a volume here, and a volume here, and a volume here, and a volume here. Now, what did we find before? When I went from this volume to another volume, what was between? That's right, it was a node. So if I'm starting here, I'm going to pass through a node. I'm going in this, just in this plane. So if I start z, positive z-axis, I've got a value. When I get over here, I'd have 0. So it diminishes until I get to the node, goes to 0, and it starts to increase, becomes a maximum at this little donut in the middle. Then I'm going down, down from here, and here somewhere, it's going to go through a node, and it's going to come back, go through another node and come back, go through another node and come back. And these nodes are going to create volumes, and they're going to create nodal surfaces. So the wave function is positive in this region of z. It's negative when it goes to here. And of course, it's going to be positive again down here. And then it's going to go back to negative and back to positive. So now notice something about this orbital. It's different from the p orbital. If I took a value right here on the p orbital that was positive and reflected through the nucleus to the other side, it would be negative down here. It turns out to be this one, though. If we do that, if I go from this point on this orbital to this point down below through the nucleus, it's the same sign. So it's symmetric going from one side through the nucleus to the other side. The p orbital is opposite. It's anti-symmetric. It changes sign from any one point you have to go to across the nucleus to the other point. You get an opposite sign in the p orbital. It's antisymmetric. So this is another kind of symmetry. The s orbital was symmetric. It's the same everywhere. Reflection through the nucleus gives the same sign. P orbitals are antisymmetric. D orbitals are symmetric. F orbitals would be antisymmetric, and so forth. So there's a pattern here to this that's understandable and really makes kind of sense in one way or other. Okay, now, so if I look at nodes, I'm going to have a conical node down here, 45-degree cone will be the node for the bottom. There will be another conical node at the top, and then another node at infinity. Well, why in the world did we get 3? N is equal to 3. When n is equal to 3, there's 3 nodes. One's at infinity, and 2 others are inside the atom. So there's always any orbital that's going to have n values of nodes. So n equals 1 has 1 node at infinity. N equals 2 has 2 nodes, 1 inside, 1 outside. N equal to 3 has 3 nodes, 2 inside, 1 outside. N equal 4 is going to have 4 nodes, 3 inside, 1 outside. It's going to always be like that. Okay. Okay. Now, there's 2 other types of d orbitals. There's one that is similar to the one I just showed you. Remember, it had values on z and a little bit on x and y. But the orbitals values was maximum on the coordinate axes. So that one is like that. The z, 3dz squared it was called. That tells mathematicians something. It just tells us that's its name. You know, I could call it Fred if I want to, and I could call this one Mary. Okay, doesn't matter. The orbital looks like this. It's going to have again 4 pieces when I go around it. Now, if you remember, the d orbital just looked like it was 2 pieces, but if I went around it, it went like 4, didn't it? You know, went through the top, went through the ring, went through the bottom, went through the ring, went back to the top. It's like 4 pieces. Same thing is here too. When I go around this XY plane, I go through 1 piece, 2 piece, 3 piece, 4 piece. I'm going to get 4 pieces here as well, separated by nodes. Now the nodes in this case, again, it's still going to be symmetric. If this one's positive, that one's negative. If that one's positive, this one has to be negative. And if that one's negative, that one has to be negative. So they are symmetric. Now this guy's name is 3D x squared minus y squared. Now, remember the first one was called 3D z squared, and the other one with the similar type of shape with intensity on the axis is called 3D x squared minus y squared. Now that just tells the mathematicians the type of transformation you have to make in order to do this graph. But for us, the first one was Fred and this one's Mary. Okay, these 2 different types. That's their names. But you do need to remember the 3D z squared and the 3D x squared minus y squared. And the square of the wave functions puts the density on the coordinate axis. One of them puts the maximum amount of intensity on the z-axis and a little bit of the intensity or density on the xy plane. This one puts the maximum on the coordinate axes and nothing in between where the nodes are located. Now, I'll draw these nodes in pieces because they tend to disappear or get mangled. This node between this one and this one is a plane, 45-degree angle plane between, in this case, the positive z and the negative y is this part of it here. And then the second node is going to be between this negative y and positive x. It's going to be that plane. So there's these two planes, and the third node, yep, it's out at infinity. So this is the shape of this particular orbital. Now, there are 5 of them altogether. We've looked at 2. 2 of them are orbitals that have maximum electron density on the coordinate axes. Now, the coordinate axes are where atoms are going to bond. Say, if this atom is going to react with other atoms, they're going to go right here and not there. Okay? So they're going to bond on to these regions. It's important that you understand that, especially when you get to, I guess, inorganic chemistry, they'll deal with this in great detail. But if I put an atom on this axis and one on this axis, this set of orbitals gets influenced greatly. If I put one up here, the dz squared orbital would would be involved greatly. So I could put 6 things around this atom, and they would bind essentially to these 2 states. And if I made this a negative charge, for example, that negative charge would repel well, put it here. Say I put a negative electron here. Remember, this is an electron. Forget about that sign there. But if I put a negative ion right here, and this is an electron, they would repel each other, which means the energy of this orbital would go up if I put something on the coordinate axes. Okay? Now, let's look at the others. There are 3 others, and they all look just like this. There's 4 lobes, just like we said. And this one is the 3D-YZ. So it's the one between the Y and the Z axis. So this X is coming out of the screen towards you, and everything you see is flat inside the screen, right at the screen level. So this one then is going to give you a orbital that has electron density between the coordinate axes. Now, if I brought electrons or charged particles along the y-axis or the z-axis or the x-axis, they're not going to be directly involved with this. The system would be stabilized, though, because of the bonding. So this energy, this orbital would go down in energy if I put something on the axis. If I put something between the axis, then it'd go up in energy. But generally, I'm going to have a choice of putting it on the axis is the way we're going to define it. And that's going to make the 2 orbitals we just looked at, energy go up. And it's going to make these 3 orbitals that I'm talking about now, energy go down. And by the way, the reason why all of those solutions that you do and observe in lab, for example, if you dissolve copper in water, it's blue. If you dissolve nickel in water, it's green. If you dissolve chromium compounds into water, it can be several different colors depending on the charge number for the chromium. You can get yellow or green or blue or some other colors. The reason for that is this spacing that is produced by forming that compound and putting it into water. That spacing splits these d orbitals so that the gap between the 2 that went up and the 3 that went down corresponds to an energy that is available in the visible part of the spectrum. So we're able to see these colored things is because of what we're studying right now. Reason why transition metals are so highly colored is that the transition metals have electrons in their d orbitals, and when they form compounds, these orbitals split apart and allow for the color. Again, it's symmetric like we saw before. All of them would have to be. And we've got a node here, and then the other node is there. And again, if I'm tracing around, plus, intense to 0, intense to 0, intense is higher, and lower to 0, and higher and lower to 0, and back to higher and so forth here, and then lower and back to higher. The node separates each one of the pieces of the orbital. So again, sort of a general way to understand this is that if I gave you a map of one of the orbitals and said draw the nodes, all you got to do is put a nodal plane in between each of the pieces. So here's one set of pieces, and here's another set of pieces. There's a node in between. Here's a set of pieces, and here's a set of pieces. There's a node in between. So these all look like this. It's a 3D YZ. There'll be two others. They'll both look just exactly like that. Now, this one was fairly easy to draw because all the four pieces were in the plane of the screen you're looking at. And I just had to do perspective drawings for the nodes. If I wanted to draw the 3D XZ, you know all I'm going to do? I'm going to change this axis to X, leave that as Z. This is going to be Y, and that would be the 3D XZ, the one between the X and Z axis. If I wanted 3D XY, then I'm just going to say, okay, this is X, and this is Y, and this is Z. Okay, so you don't have to try to draw all three of them in three-dimensional perspective, and you would really, really, really have a hard time putting all five of these back together. Just imagine what a complex mess that would look like. You know, it's simpler than that. You know what you get when you add all five of them back together in equal weight? A sphere. That actually happens when you add those all together and you fill them all up. When you fill that orbital up, that atom comes back to spherical shape again. Remember I told you atoms had a shape way back day one, and that shape that the atom had the moment it was created is still the same, and it does determine the different shapes and things that we can build out of those models. Imagine a box full of spheres, a box full of cubes, a box full of triangular pieces or whatever. There's only certain shapes that you could put together out of that set of stuff. I mean, if you've got squares or rectangular cubicle type things, you can pack them together and put together things. Be like using bricks to make a building. If you take spheres and start putting them together, you know you can't pack three-dimensional volume with spheres. There's always going to be some holes when you put. Imagine a jar of marbles. The whole volume of the marbles doesn't fill the volume of the container. There's spaces between the marbles. Well, so the shape of atoms determines the shape that they can be in, and the shape of molecules they can make. And that's all because of the way these orbitals are shaped. Okay. I think this might be a good time just to stop. The next thing we're going to do is build electronic structures, and that's going to be a little bit of time, and so let's just wait on that, and we'll do that probably tomorrow. Okay, I'm going to stop the recording.